Distinguished participants, welcome. I'm very happy to have this opportunity to talk about the Austrian experience with energy efficiency in buildings, and also with the implementation of the European Directive on the energy performance of buildings. Okay, my name is Michael Wabb. I'm a practicing architect and consultant with the Austrian Consulting Engineers Group. And I've got over 20 years experience in building, low energy buildings in Austria and in European countries around Austria. And we've also done consultancy work for UNDP and Jeff and the European community to spread the concept of energy efficiency in buildings throughout Europe and throughout, we've done it in Kyrgyzstan, we've done it in Armenia. Okay, the first thing we will talk about is the integrated building design and the benefits of this procedure. The benefits for the building owner is that you have reduced operating costs over the life cycle of the building. For the community, what's important is reduced strain on the utilities. That if you have a neighborhood of reduced energy buildings, of energy efficiency buildings, the utility has, you don't need to build up the utility to such the extent as if the same community had high energy demand. And naturally, the benefits for the global environment, reduced greenhouse gas emissions. Okay, we're going to talk about simulation tools in order to achieve the integrated building design. What we're looking at on the, this is the design process from concept to occupancy. And what's important to see is the great potential for energy efficiency savings in the early stages of the design, the building design. And then further in the inspection process, how important the inspections are during the construction phase in terms of building up the potential savings of energy in the building. The important part here is the integration, that you have all of the participants in the building process working together in order to achieve a target. Okay, important for the simulation program is that it incorporates all the local climate data and that it incorporates a standardized use profile. That means for residential buildings, for example, that the indoor comfort temperature is around 20 degrees, the amount of ventilation necessary, the schedule of use, the warmth generated by equipment, the occupants, this all has to be taken into consideration. And also the form and orientation of the building, what solar radiation gains are expected, and naturally the building insulation, but as important, the thermal mass effects, that is the storage of warmth or cooling in the building material inside the thermal insulation. Okay, I'm going to show you an example of the Austrian form for calculating the energy performance of buildings. This was developed by the Austrian Institute of Civil Engineering, and it was made available free to all building professionals over the internet. Okay, important on the cover is determining the location of the building. And what we've got over 2,000 locations in Austria are documented in terms of the climate data, in terms of the solar radiation, in terms of the heating degree days. So this climate data feeds into the program, into the Excel program. On the next sheet in the Excel form, you talk about the type of building. In this particular case, we're looking at a multifamily residential building. And then we talk about the type of building, whether it's a light construction or whether there's the building materials are concrete and masonry, which can be used to build up the thermal mass of the building. And then at the bottom you see the brutto, the volume of the building, the heated volume of the building, and the heated floor area of the building. This is the calculation for the heated volume and the heated floor area. And what's important in the calculation is that each of the exterior surfaces of the building volume, basically this is the heated building volume of this particular project. And further on in the project, each of these surfaces, as seen here, will be described in terms of the thermal quality of that exterior surface. So we talk about the building volume and the external envelope. Okay, in this particular case, we're describing the first one of the compositions of the building envelope in terms of the U value, and each element in the construction is described and contributes towards the U value. Then we talk about the area of each of these of the building envelope, each of the pieces of the building envelope, which will in the end describe the complete thermal envelope of the building. We talk about the windows and the U values of the windows. You have the option here of either presenting a certificate for the complete window or describing the glazing, the frames, and the thermal bridge of the thermal frame. Then you describe the window areas, and what's important here is the size of the window, but also the orientation of the window, if it's facing south, and whether or not it has external shading devices attached to it. We have the same for exterior doors, basically the U value of exterior doors and sizes. Okay, and then we talk about the thermal bridges. Basically, the form allows you to either calculate the thermal coefficient of the thermal bridges, or to take a variable, an assigned variable based on the European Commission documentation. The same is true of the ventilation, and here you're given the choice whether to describe manual ventilation or mechanical ventilation. Okay, and based on all of this information inputted into the program, you come up with the energy certificate of the building. In the case of Austria, it's concentrated on the heat, yearly heat necessity, the heat demand of the building. In this particular case, we've got 37 kilowatt hours per meter squared per year. Okay. We use this program, as I say, this program was made available to all building consultants over the internet, and we use this program to experiment with the building form, with the building, with the composition of the building shell, and we can compare the effect of adding additional insulation, adding improved windows, and also with the ventilation. And the idea is that you can determine the optimal energy efficiency measures using this program in order to have the most cost-effective building construction. That we're basically aiming at a life cycle, or not a life cycle, but a 10-year payback period for the measures incorporated in the building. Okay, and some of the concepts behind building energy efficiency buildings. Basically design measures that you can use at the beginning of the design process, choosing the proper orientation of siting and orientation of the building to optimize the solar gains, optimizing the form and compactness of the building. And by compactness, I mean that the ratio of building envelope is reduced in terms of comparison to the useful floor area of the building. And finally, whether in a community you can place the buildings in such a manner with landscaping in order to create synergies between buildings and the landscape to reduce the energy demand of the building. The other issues are creating inside the floor plan of the building to create comfort zones. That means creating heated and cooled zones within the building that are compact and have individual control. And again, in the considering the design of the building, considering the location of these heated and cooled areas in terms of solar exposure, in order to reduce the heating and cooling load. And then coming back to the thermal mass of the building, considering that the building substance, the concrete, the masonry, inside the insulated layer can store heated and cooled air, heated and cooled temperatures that are, you can store these up during the night, for example, and then they can be slowly released over the course of the day. In combination with this idea that you have intelligent regulation strategies, that means that you use a time, for example, to provide cooling. You use cool air during the night in order to cool the structure of the building, that again can be released slowly over the course of the day. Okay, again, the most effective means of saving it, one of the more effective means of saving energy is to use heat recovery. Basically, you need the ventilation for the building to create a healthy environment. And on top of that, the expelled air we should extract either the cool or the heat from the expelled air in order to precondition the intake air. And then the importance of inspection in the process again, that on-site inspections to ensure the quality of the thermal insulation, that the building is airtight, that there are few thermal bridges or no thermal bridges, that the mechanical systems are constructed in accordance with the certification. Yeah. Okay, and then during the operation, it was touched on earlier today, during the operation that you have individual regulation and control within apartments, within office spaces, that the people in the apartments can control the temperature. And in combination with that, billing by consumption, that the tenants realize that if they want excessive cooling during the summer or excessive heating during the winter, that this has an impact on their heating bill. And another important aspect is that the tenants are informed about how to use their building, that they realize the best practices in terms of energy efficiency, and that we can achieve through distributing user manuals to the tenants, to having training for the tenants. And then once the energy demand of the building is reduced, we can begin to look into the use of renewable energy sources in order to meet the demand. Some examples, using solar thermal systems to not only generate warm water but also heating. Another important system that is quite popular in Austria now is the geothermal heating and cooling, using earth pumps in order to precondition the heating, the air coming into the building. The other possibilities for electricity, using photovoltaic, with the possibility of integrating them into the architecture. There's a possibility in terms of photovoltaic in Vienna that you can feed these back into the utility grid. You can use them independently or feed them back into the utility. And then again, reducing the energy load also includes reducing the electricity loads for the building, using energy efficiency lighting and fixtures, optimizing the use of daylight inside the building, and using timers and individual controls to reduce after-hours lighting in offices and residential. The other important aspect is that if you have an energy efficient building shell, you can talk about reducing the mechanical systems required for the building. And then again, the regulation, ensuring that the heating and the chillers are used according to the optimal times and the needs of the zones. And choosing naturally energy efficient appliances inside the building. Okay, the first consideration that we spoke about this morning were about using the local climate and considering the climate in the orientation of the building, especially considering solar exposure to the building and how to prevent overheating in the summer and to use solar radiation in the winter to help provide heating. Okay, we talk about the different climate zones in Europe. In the northern climate, you have a high space heating demand and low solar radiation, especially during the winter, so you have little opportunity to use the solar radiation to help you heat the building. In Central Europe, where Austria is located, we do have space heating demand, especially during the winter, little cooling demand, and enough solar radiation year-round that we can help supplement the heating with solar heat gains. And finally, we talk about Southern Europe, where Istanbul is part of this, where you have high solar radiation year-round. You have need for cooling more than heating. This is the idea. Okay, this is an example of a building we built in Austria. Important to illustrate siting of the building. The building is built, it's a residential building built into the south-facing slope of a hill in Graz. And what this allows us is very much south exposure and a very reduced northern exposure for the building. And what we've done on the south side is we have, you can see it in the photograph here, we have a full floor-to-ceiling glazing, but with an overhang on each floor of 60 centimeters to prevent, to help shade the window area. And you can see these lines here. This is the summer sun angle, and this is the winter sun angle. So in the summer, you don't have solar heat gains on the inside space. The window is kept in shadow, but in the winter time you have solar radiation coming into the living space and helping to heat the rooms. And further, each of the windows apartments has the possibility of putting down blinds on the outside, solar blinds, outside of the window area. This further helps the occupants to regulate the heat gain, especially during summer. A further concept is the depth of the building. Here we talk about, it's a good illustration of the compact layout. Basically, we're looking at apartment units that are 18, 19 meters deep from the south to the north. And we achieve this by having the important rooms that need lighting, the living room, the bedrooms, located on the outside, and having the service core, bathrooms, kitchen, located on the inside where the natural daylight isn't required. And further, the living rooms where where the occupants are spending their daytime hours are located towards the south side. This is the rooms which require the most conditioning, and the bedrooms are located on the back side, on the north side. These can be cooler during the day. Okay, this is a further example. These are the SOS Children's Village in the Czech Republic that we worked on. Again, you can see on the south side, we have floor-to-ceiling glazing. And on the north side, we've put the service rooms, the bathrooms, the kitchen areas, the storage rooms in the building. And on the south side, we have the main living room and bedrooms for the children. And in the section, you can see that, again, the floor-to-ceiling glazing on the south side, and on the north, east and west sides, as little window area as possible. And further, we've provided this 60 centimeter balcony towards the south again in order to, and louvers to help provide shading, natural shading from the heat gains in the summer. Okay, now I would like to speak about the building envelope. It has two aspects. We talk about the insulation, we talk about the air barrier. And for the concept of the building, it's important to first attack the energy efficiency of the building before looking at the efficiency of the heating and air conditioning systems. It's important that the building itself, the composition of the building itself is energy efficient before we begin applying energy efficient equipment. So in that respect, we talk about an efficient separation of the outdoor climate from the indoor climate. That means no movement of thermal movement and no air movement through the building shell. Okay. Again, the key considerations about optimizing the building shell, having a compact building form, trying to get the maximum usable floor area with the minimum of envelope. In the building shell, ensuring that you have continuous thermal insulation and avoid any thermal barrier or thermal bridges across this insulation layer. And important in areas of high humidity, having an airtight envelope, building envelope, avoiding the transmission of air and moisture through the building envelope. And finally, the quality of the windows is important, that you can optimize the amount of natural daylight, but at the same time you can restrict the solar heat gains during the summer and use them during the winter. Okay, just an illustration again for the compact building form. The strategy is to reduce the amount of external building envelope while maximizing the amount of internal usable area. And the picture on the right shows the SOS Children's Village home. You can see the fully glazed south facade and the insulated and closed east facade. And further, you can see on this building the south-facing shading construction. This steel frame is attached to the south facade. It's got a depth of 60 centimeters and provides the framework for the louvers. This is what we're trying to avoid in terms of compact building form, that too many projections and bays into the building form increases the amount of surface area of the envelope. This is another example of a building that we did, a low energy housing project that we did in Graz, Austria. Again, we have on the south elevation, we have the full glazing, but with external shading. And on the north elevation, we've reduced the amount of windows to a minimum. We've located the bedrooms, the kitchen, and washrooms to the north side. And further, we've optimized the depth of the building by locating service rooms like the washroom on the inside of the where no natural daylight is required. Okay, now we talk about the shell itself, having a continuous layer of thermal insulation around the heated volume. Again, this is the SOS Children's Village. In this particular case, we have 25 centimeter concrete, clay block, and 20 centimeter of insulation on the outside. And important is the idea of building up a good thermal mass inside the insulation layer. You can see it in the floor plan. it's naturally broken for the floor-to-ceiling windows along the south facade and for the smaller windows along the north, east, and west elevations. This is showing the application of this 20 centimeter insulation blocks to the outside of the building. In this particular case, we're looking at the 20 centimeter blocks being adhered to the clay block. You can also see that the windows are being constructed in such a way as to be integrated with the thermal insulation. You can see that they're actually outside the layer of block. They'll be finally integrated into the insulation layer. Just an illustration of the outside wall. You can see the 20 centimeters insulation and the 25 centimeter clay block. And important that at the details at the meeting of the roof and the wall, the meeting of the floor slab, and at the ground, that as far as possible we try to get the insulation layer as continuous as possible. And that means preventing thermal bridges. These are places where for example, where the floor slab goes through the insulation layer, allowing the heat transfer from inside to outside. So we have a few examples of how to avoid thermal bridges for balconies, for projecting balconies. In this particular case, you can see the prefabricated insulation and reinforcing bar construction that is integral with the concrete floor slab. So in this particular case, it's a compact insulation, and the reinforcing bars are integrated in the insulation and poured with the floor slab, so that the whole balcony construction becomes an integral but insulated structural component. And this naturally allows the reduction of thermal movement from the outside to the inside. This is another example of a balcony construction. This was an existing building, and what we did is we had to apply an insulation layer on the outside of the building. So what we've done is we've mounted steel brackets to the outside of the building and hung a steel balcony construction on these steel brackets. Okay, the other issue is the air barrier, and this is very important, especially in humid climate, that you prevent the outside humid air from passing through the construction of the building and causing condensation inside the building shell. That means we have to ensure that it's sealed around windows, it's sealed around electrical outlets, and all the details where the roof and the floor slab meet. Okay, and to test the thoroughness of the air barrier, they have a test for the passive house inspection called the blower door test. And basically they apply a positive and negative pressure to the building. They close all the windows and apply this testing component to the door. And once you have the sealed building, naturally you still need to account for ventilation. And this is done in the passive house standard. It's done through mechanical ventilation. And the reason for that is that it requires heat recovery. It requires, first of all, the level of ventilation, but secondly, that you can apply heat recovery or cool air recovery system that takes the energy from the expelled air and applies it to the intake. And naturally, the windows play an important role in this. Typically, we're working with values of 1.1, U values of 1.1, passive house around 0.85, looking at triple glazed and high efficiency windows. Okay, this is again the SOS Children's Village that we did. You can see the U values of the window that we've applied here. We were using a 1.1 U value for a passive house. Again, you need a 0.85. Important here again, the windows themselves play an important role in continuing the insulation layer. Around the windows, we have to accommodate, we have to ensure the lack of thermal bridges around the windows as well. And this is why we're overlapping the insulation layer over the window frame, over the insulated window frame, by at least 3 centimeters in order to reduce the thermal bridge at the window frame. In the earlier slide about the insulation, we saw how the window frames were actually outside of the block wall. This is a typical detail in passive house standard to further increase, to further prevent the thermal bridge around the window frame. Again, the strategy that we try to employ is to reduce the energy consumption of the building as far as possible. And in the case of passive house, we're looking at reducing it to as much as only 17 kilowatt hour per meter squared per year. And then finally, the rest we can begin to search for renewable energy sources which can cover that demand. And again, we're looking at possibilities to use solar radiation to help with heating, but also cooling, using photovoltaics to help generate electricity for the building. For both heating and cooling, we use the ground source heat pumps or air source heat pumps. And again, for electricity, any uses of wind generation. And finally, in order to supply the backup systems, we're looking at sustainable sources of energy, using district heating and cooling to help supply the building, using natural gas instead of coal, for example, and looking for electricity from renewable energy sources such as hydroelectric. Okay, the final part of the presentation, I'd like to talk about passive house building standard and show a couple of examples. The reason is that the European directive has been tightened, and the new directive, Energy Performance Directive, talks about net zero energy buildings. So when we talk about passive house, we're talking about a step in the direction of net zero energy buildings. This example is the Austria house, the Austria Pavilion for the 2010 Winter Olympics in Vancouver. In this particular case, you can see in the section the continuous insulation layer around the building, and further the glazing directed towards the south. You can see that the glazing, the windows, have a U value of 0.74, and the heating demand for the building of 15 kilowatt hour per meter squared per year. This is a second example of a passive house building, a student dormitory in Vienna. In this particular case, the amount of window has been reduced considerably. And further, each of the rooms has the possibility of closing. They have a sliding door located on the outside of the building that they can shut the window completely during the summer. The building has a depth of about 18 meters again, and they've achieved this again by putting the service rooms on the interior of the building. They've achieved this by putting the service rooms, kitchens, bathrooms, on the interior of the building. And further, they've put light wells through the building to help light the interior spaces. So here you can see the slide on the left. You can see the light well moving through the corridor area, and the kitchen area inside the unit is basically supplied by the light from this light well. Here's a section through the building. Again, you can see the continuous insulation layer around the building, and the natural daylighting through light wells. And further, the building energy system is partially supplied by a geothermal system located under the floor slab of the building, and then a heat recovery system located on the roof of the building. This is an illustration of the typical unit. Again, you can see the geothermal system helping to supply the heating and cooling load, as well as the heat recovery equipment. And further, the use of natural daylight to help heating of the space. Not only the natural daylight, but also the occupants themselves, the equipment enclosed in the space. These are all heat sources that are inside the insulated layer that help to contribute to the heat demand of the building. So this is an illustration of the heat energy being supplied to the building. So in the first column we have the transmission losses through the building envelope, and in the second column the ventilation losses through the ventilation system. And compensating for that partially are the solar heat gains and the internal heat gains. And by the internal heat gains, we're talking about heat generated by the occupants themselves, by the equipment in the space. And then we look at the additional heat required then after these solar gains and internal gains, what the heat energy demand considering different room temperatures. So you can see the difference in heat energy demand based on increments of 1 degree additional internal temperature required. What we've been able to achieve with the Passive House student dormitory are savings of about 80% compared to conventional buildings. And the building itself required about 6% higher construction cost, and we talk about a payback period of about 10 years in order to compensate. Okay, as I mentioned earlier, the new European directive talks about moving towards near zero energy buildings. This Passive House standard is a step in this direction. You can see the development of the Passive House building standard in Austria over 20 years. Another important factor of the Passive House is the strict certification requirements. The inspections, not only the design but also the inspections for Passive House are much stricter than for standard housing construction. Okay, that's the end of my presentation. Thank you very much.